finished up alkenes. So now what we're going to do is move into pretty much extended alkene structures. Okay, so I came up with the strength in numbers argument here. So we're going to look at the benzene reactivity. It's kind of its own separate branch as far as the chemistry goes. So we don't see a whole lot of overlap. So you guys should have finished quiz 7. We got quiz 8 coming around now. And you'll notice quiz 8, the very first page, has a whole lot of those questions that nobody likes, where it's predicting products, reactants, starting materials, depending on the information given to you. Okay? Everything we've looked at so far is ultimately summarized in those types of problems. So you should be able to go through and do all of those problems. And I don't expect it to be easy at this point. What I do expect you to be able to do is work at it and start to build your memorization skills with those reactions, so that when you see an alkene and bromine, you know that bromine adds to the double bond and you get an addition reaction. Okay? So the idea is to look for those patterns, start to build that muscle memory so that you can go through it faster when it comes to the exam. That's largely why the quiz, or why I'm giving you these quizzes, is so that you can work on getting that practice, forcing you to do that practice every week as opposed to the homework. Okay? Along the lines of the homework, we've got more homework problems. Yay, homework. Okay? That looks like a decent amount of problems, and to make matters worse, it's even more because a lot of those are very multi-part. Okay? So you're looking at probably each of those being 5 to 10 pieces within each of those questions. Okay? The idea is practice, because practice can get you through this material better. Okay? So, let's take a look at our Benzene Basics. Okay? And this will come back to the last quiz, which dealt with the heat of hydrogenation. So if we look at an energy diagram for some basic structures here, energy is going up on our left-hand side, and what we're looking at is increasing the energy. So if we compared an alkane, which is what we've got down at the bottom, and we want to compare that to, say, the next structure. What's changed? Bond. So we've got a pi bond. I don't want to write it there. So we've got higher energy. We've got some reactivity. So if we were going to look at the energy and compare these, I've got that structure drawn slightly higher. Okay, and what we're looking at is an alkene, okay, for that single double bond between two carbons. What happens when I move to the next structure up? I now have two alkenes. What does that mean for the reactivity? It's going to become even more reactive. So I would end up drawing that structure even higher. If we move even higher up, we move in with 3 double bonds. What happens? It's even more reactive. Okay? So we're starting to put more and more reactivity into our structure because we're putting in more reactive bonds. Okay? So that's one of the patterns that somebody went through and discovered and said, okay, as we add more double bonds, it gets more reactive. Okay? And then they went through and did that with benzene. Okay? And they took a look at that structure, and they ended up finding out that that structure is actually lower in energy than what we would predict for a 3 double bond system. Okay? That lowering in energy is where we came up with benzene and why it has all sorts of special chemistry, and it moves and changes its reactivity from a standard alkene. Okay? So that's why we have to treat it slightly differently. So if I tried to react this with bromine, okay, if we went through and did an alkene reaction with bromine, what would our product be? What would we expect? Well, just the alkene. Over here in red now. 3D.
That pi bond will be eliminated?
I don't like your phrasing, but you got the right idea.
The pi bond will be used to interact with the bromine, so you'll have a sigma bond.
So we end up changing our pi system. We lose the pi system, and now we've got sigma bonds through it, and we've added, which is the word I was looking for, bromine across the double bond. Okay? So the type of reaction we did there is an addition reaction. If we went to the aromatic ring and tried that same reaction, Okay, what might we expect?
Similar, but in a ring form.
Similar, except we're adding the bromine to the ring. What do we actually get? What reaction happened here?
Addition.
If it's an addition, what happens in the addition?
You add something.
We add two pieces. Both those bromines, we take our benzene and our bromine molecule and we smash it into one molecule. Do we have one molecule? No. We have two molecules, so it can't be an addition reaction. I'll give you another clue. The other piece that's missing.
Substitution.
It's a substitution reaction. Okay? If we look at our benzene to start with, it's got 6 carbons and 6 hydrogens, all coming off of those individual atoms, right? If we move to our product and we look at the carbon where our bromine is attached, whisk guard. It's all right, let's see what I can do. Move. There we go. That carbon, how many bonds does it have?
3.
4 bonds. We've got the double bond, there's 2, and then 2 sigma bonds, 4 bonds. Is there a hydrogen attached to it anymore? No. Okay. We did a substitution reaction. We substituted hydrogen for bromine in the process of this reaction. Okay. So that was potentially one of the first red flags that popped up, and they said, okay, something's different about this structure. Okay. So there's a few arguments that we could use to evaluate why benzene is so different from a double bond. Okay. And everybody's favorite answer to most questions is what? Because. Touché. No, that was the least favorite answer. No. What's the answer to nearly everything in organic chemistry? Electronegativity is a good answer. Sorry, not this one. Stereochemistry is an answer that we want to avoid as much as possible. Hybridization is part of it, but that's also not as important. Electronegativity is a big answer. What's the other big thing that when I ask you to compare two atoms? Size is another big answer. And if we don't have a difference between electronegativity and size, we have to look even further. No. Resonance. Which we would show by using that double-headed arrow. I wrote resonance. There it is. Okay. So we could go through and say the electrons move from one position to another. And we could draw out that resonance structure. We put a positive charge on that carbon and a negative charge on that carbon. Okay. Is that a good structure?
No.
Why not?
There's charge.
There's charge. We don't like charge. Okay. So typically when we look at alkenes, we don't evaluate those charges unless we're looking at reactivity. Let's go through and do that same idea with our benzene ring. So let's take the electrons in that pi system and let's move them. How many bonds does this carbon now have?
4.
If I move the double bond over. It has 5. So then I have to break a bond. So let's take the electrons in that pi bond and move them over there. How many bonds does that carbon now have? 5. So let's move electrons over there. How many bonds would that carbon now have? 4, because we already got rid of that first pi bond. So what's our structure look like now that we've settled on where all our charges are? We've moved a double bond there. We moved one here, one here. Drawn resonance. Which of those two structures is more stable? Neither. Why? Neither one is charged. Okay? So when we looked at alkene reactivity, we're looking at that resonance structure to look for our source of reactivity at first, and we see that we find charge, and we can find something reactive. When we move to the benzene structure, and we look for our first resonance structure, what happens? The exact same energy. I get two structures representing one compound. What does that mean about the stability of that one compound? Becomes a lot more stable. Okay? And it's due to the resonance within that system. What we've got in this structure is conjugated double bonds. That means the double bonds can shift. Okay, they're one sigma bond away from each other. So we can count them out. There's a sigma bond there, there, there. One sigma bond away from each of the double bonds. We could go through and do the same thing on our resonance structure, and we could see again that we still have that one sigma bond away. Okay? Due to that proximity, the electrons can be pushed from one position to the next, or one bond to the next. Okay? To do that, it's not just the conjugation, but we also have to make sure that the electrons, or where those electrons are, which is what type of orbital. The electrons in our pi system are in what type of orbital?
P.
They're in a p orbital. Okay, so if we looked at it from the top, we would just see our 6 orbitals. If we looked at it from the side,
Three.
Let's see if I can draw this. Our p orbitals are all aligned with each other so that that electron density can be shared all the way around the ring. Okay? So what we're starting to see and recognize is that there's an increased stability due to that orbital overlap that's been conjugated across multiple atoms. Okay? Famous guy went through and looked at this and came up with a couple rules. Okay? That guy was Huckel. So you end up getting Huckel's rules for aromaticity. Yes. Yep.
Can you go back a little bit?
Yep.
Is that benzene ring equal in energy to that, or is it between those two?
I didn't do a very good job, and I didn't have the textbook with me, so look at your textbook to figure out the exact energy difference. I'm pretty sure it's higher in energy than the double bond, but definitely lower than the triple bond. Okay. So Huckel went through and looked for certain patterns. And so when we look at benzene, the very first thing we can see is that it's cyclic. Okay? So that's going to be one of the important rules for this to work. If we looked at our triple bond previously, okay, if we look at our triple bond up there, we don't have that cyclic structure. We don't get the same stability that we would get from our resonance stabilization in our benzene. Okay? So our first rule is it's got to be cyclic. We have to have a p-like orbital on each atom. Okay, we'll come back to what I mean by p-like in a second. Okay, but we can look at it ultimately as being a p orbital. What is the hybridization of every atom in benzene, or every carbon atom? sp2. So what atom is, or what orbital is left over? A p orbital on every single one of those atoms.
Now when it says have a p-like orbital, does that have to be an unfilled orbital?
It has to have a p-like orbital. Just leave it at that. As far as electrons being in it versus not, we'll cover that with the last rule. Okay? Our third rule is that we have to be approximately planar. Okay? We need to be planar so that the electrons from one p orbital can overlap with the next. If you guys vaguely, maybe not vaguely remember, we looked at what's referred to as cumulene. And one of the questions I asked a long time ago was, our hydrogens, are they in the same plane or different planes? They're in different planes, and it's all because that carbon in the middle is sp hybridized. The p orbitals, those double bonds, are not in the same plane. They're in perpendicular planes, which means the electrons in those two double bonds can't overlap, can't interact with each other. Okay? We have to have p orbitals parallel to each other, okay, to get that maximum overlap. And then our last rule is we have to have 2, 6, 10, 14, etc. pi electrons. Anybody really good with numbers and can see the pattern between 2, 6, 10, and 14? Were you really that good, or did you just read it?
Well, leave that up to you.
Okay. You're really that good. I like that. That's a good job. Okay. We end up with 4n plus 2 is our general rule, so we can expand out to a whole heck of a lot more electrons. And as long as the rest of our rules are satisfied, we can be aromatic. So all of these things contribute to it being an aromatic structure. If we go through and evaluate benzene for that last one, okay, how many electrons are in the pi system? Okay, so where are our pi electrons to begin with? In the pi bonds. How many electrons go into a single pi bond? 2. We won't count the sigma bond that's also involved in the double bond. We're only counting the pi bond. How many electrons are in this pi bond? 2 plus 2 plus 2? 6. We satisfy our last rule. Okay, we have 6 electrons in that pi system. Okay? So it's a question of applying these rules consistently. And what he ended up finding out was that the stability that we find in benzene can be found and applied to other structures as well. Okay? So one of the things that you need to learn or pick up from this chapter is applying this rule to find out if structures are aromatic or not, because that lends something to stability. If we know something about stability, that tells us something about reactivity. Okay? So let's go through a couple examples. Let's take a look at cyclobutadiene, which is the next one there. Aromatic or not aromatic?
No.
Okay, why is it not aromatic? Okay, it's cyclic, so that rule is fine. We have p-like orbitals on each atom. Each of those carbons is sp2 hybridized. It is planar. There's nothing we can do about that. And then it has how many electrons? 4 pi electrons. That does not match our rule number 4. We have to have 2, 6, or 10, which means it invalidates Huckel's rule. We're not aromatic. Okay, does that make sense? Mm-hmm. What happens when we move to the next structure?
No.
Why is that one not aromatic?
It's not p-like orbital and everything.
We also have 4 pi electrons, but before we even get to that, what's the hybridization of that carbon?
sp3.
sp3. Do we have a p-like orbital there? No. Okay.
What? I don't understand. Why not?
What's the hybridization? sp3. Okay. To have a p-like orbital, we have to have either a p orbital. At this point, we have to have a p orbital. If it's sp3, we've taken the 4 atomic orbitals, 1 s and all 3 p's, and turned them into new orbitals, sp3 orbitals. Do we have a p orbital anymore? No p orbital. So we don't have a p-like orbital. Okay? And that's what we ultimately need to be referring to or looking at in this case. And we're going to look at an exception to that the way end of this series of examples.
So p-like orbital will usually be like sp2?
So the sp2 isn't our p-like orbital. What's our p-like orbital in the case of the sp2? It's the p orbital. It's the leftover p orbital. Okay. If we're looking at an sp3 hybridized structure, we've gotten rid of all of the p orbitals. How can we have a p-like orbital if we don't have any p orbitals?
That's why it confused me, because you said whether it has electrons or doesn't have electrons doesn't matter, but it kind of does, because if you have an extra p, there's no electrons in it, right?
I do see where you're going with that, and that's
why I was confused.
and where it comes in is kind of the exception with these structures down at the end. Okay,
I'll just look.
and since we'll come back to that.
Okay.
Okay, so I want you to look at it first for a p orbital. Does it have that p orbital left over? If it does, great. Okay, if it doesn't, then it can't be aromatic. Okay, taking a step further, if we look at our bonds out there, can we move these electrons anywhere? Okay, the electron, let's try not highlighting in red. Those electrons. If I try and move those via resonance into the ring, what have I done to the bond to that hydrogen? I've broken it. Do I have resonance? No. Okay, does that kind of make sense? So you have to look for the availability of those electrons. And in this case, we have an sp3 hybridized carbon, okay, which immediately says, okay, p orbitals are gone. Can we make one of those other orbitals do what we want it to do anyway? No, because then we break a bond. Okay? Kind of makes sense?
Yeah.
Okay. What happens in the next case? Is this structure aromatic? It's cyclic. Do we have a p-like orbital on each atom? Yes. To have a positive charge, carbon has to be sp2 hybridized. Okay, so we have a leftover p orbital. Okay, is it approximately planar with the p orbital overlap? Yes, we have that too. How many pi electrons are in this structure? 4. Double bond there, double bond there, which means not aromatic. Okay, how about this one? The next one. Why not there? Not cyclic. Okay, you getting the idea? Apply each of the rules. Start at the top because those are easier and work your way down to the more difficult ones.
What does that mean, approximately planar?
I don't like that rule either. I'll show you where that came from or comes from in a second.
So on the test, we can just assume you won't give us one where it's approximately not planar.
Yes.
Okay. Fair enough.
Do we have another question somewhere? Okay, how about our next structure? This is one that gets weird. Is it cyclic?
Yes.
P-like orbital on each atom. Here's where it gets dicey.
Yeah, oxygen is the sp3, isn't it?
It's sp3 hybridized, which would mean no p orbital. So we could jump to the conclusion that no, it's not cyclic.
And you have resonance.
However, we're wrong because we do have resonance in this case. If we go back to the case that we had before, where we still had that sp3 hybridized structure, we couldn't touch the electrons in those carbon-hydrogen bonds. Okay? And the reason was that we couldn't move them because if we did, we broke a bond. We can't break bonds. If we go back and look at our oxygen here, we can take a look at those electrons. Can we move those electrons? Yes. We're allowed to move lone pairs. So I can move those into the ring. But it's not a p orbital. That's where the p-like comes from, is dealing with what's referred to as heteroatom structures. Why do we call them heteroatom? Right idea. The oxygen and the nitrogen, okay, atoms within the ring are not carbons. So we'll refer to it as a heteroatom cyclic structure. Okay? So, back to the problem at hand. We just said that those electrons were available for resonance, but they aren't officially in a p orbital. So what's going on with that? What would you expect? Should this structure be aromatic or not aromatic? Not, because it doesn't look like our p-like orbital. And what we ended up finding out was that it was aromatic. It is an extremely stable structure. Okay? So we came up with a theory at first that it's just p orbitals, and then we had to go through and change our theory to account for heteroatom structures. Okay? And the reason that it ends up becoming stable, I'll have to do some research, see if I can find a better picture than what I'm about to draw. We've got a cyclopentane structure, which remember has that envelope. So I'll exaggerate it. Okay, where this is our oxygen atom up at the top. Yes, no?
Yeah.
Okay, generally like an envelope shape. In that case, these electrons are certainly not planar with the rest of the structure. Those are not going to overlap our p orbitals. Okay, so based on what we would understand for a cyclopentane-like structure, we would say, no, that's not going to work. Well, the structure says, hey, if I change that bond angle and flatten out, what ends up happening? Now those lone pairs start to approximate a p orbital. Okay, they're still in an sp3 hybridized structure. Okay, oh man, how can I draw this? Let's draw the easy ones first. There are p orbitals. We have envisioned this one is coming up, kind of just directly up, and our other lone pair is aimed directly down. Okay, in an sp3 type shape. So we've got the oxygen. Okay, if we looked at my hand, the oxygen ring going backwards. My thumb and index finger being carbons. The lone pairs would be my other hand coming in the other direction, right? Okay. Our planar structure is in the plane of my hand. Okay, what happens if I tweak that structure ever so slightly? What happens to those electrons? They start to become perpendicular to the ring, which means parallel to the pi system. If it's parallel to the pi system, what can we do? We've now increased our conjugation. We can do resonance. Okay? So that's the argument for why that structure actually folds and allows those electrons into the system. It puts a little bit of stress on the oxygen because it has to change its bond angle to account for that, but it more than makes up for that stress by increasing the stability or decreasing the energy of the structure. Okay. The other option, if you really wanted to go into it, just to make it maybe easier, we'll see what you say. Resonance. Lone pairs, we can move them. If we move them in there, we end up with, say, a structure like this. Negative charge there, double bond, oxygen, double bond. What's the charge on oxygen now? Positive. What's the hybridization on that oxygen now? It's now sp2. Okay? So just by the sheer ability that we can do resonance, we end up changing the hybridization from an sp3 to an sp2, which means in our initial structure, it's not officially sp3. It is an average of your sp2 and your sp3. So that's the next question. How many of your lone pairs can actually move? So you're right, I didn't draw that extra lone pair, but how many did I show move in our drawing? Just one pair, so there's another lone pair out there. Okay, and that's going to move into our next issue. Approximately planar? Yes. We now have to count our electrons that are in the pi system. That's where it becomes trickier, okay, or more tricky. We've got our double bonds. Okay, double bond there, right? So that means 2 electrons from each, so we get 4. But what did we do with our oxygen? What happened up here? We moved electrons into our carbon ring, so we've put 2 more electrons into the pi system. One of those lone pairs was donated in. Could I donate more than 1 lone pair? Can I take this other lone pair and put it over here? What happens to the oxygen?
Oh, then it gets like super positive. It's like really happy.
Super positive. It becomes +2. Taking a step further, what's the hybridization? SP. What's the bond angle? 180. Can we fit 180 4-bonded oxygen into that? No. Okay? Only one of those lone pairs can ever get donated into the structure. Okay? I'll try and bring a model kit to try and show this on Thursday as well, so you can kind of see what happens to those electrons and where they end up shifting. As we bring one lone pair into the ring, the other lone pair necessarily has to move out of the ring. Okay, which I can vaguely attempt to do with my hands. If we've got our ring being flat, running kind of vertical here, and we look at our sp3 electrons, what happens as I rotate my index finger so that it overlaps with the pi system. Where's my thumb now aimed? Completely away from the ring. Those electrons are now in the same plane as the ring. Where are your p orbitals? Perpendicular to the plane. Can we have electrons in perpendicular orbitals interact? No. Okay? So when you look at your heteroatoms, if it starts in an sp3 system, let's erase everything. So if we compare here, if we have an sp3 heteroatom, we can count one lone pair as being able to donate into that ring. So in this case, we've got 2, 4, and 6. Is this structure aromatic? Yes.
That's confusing because like everything about it says no.
Yep.
Is it the same on any of those?
On any heteroatom structure, yes. So what happens if we move to our last example? Okay. Are we cyclic in that last case?
Yes.
Okay. Do we have p-like orbitals on each atom? Okay. So here we could go through and do our resonance argument. We do have p-like atoms here, here, and here. This nitrogen is what hybridization?
Which one?
sp3.
sp3, our top nitrogen. Okay, so we would initially say no, but can we take that lone pair and donate it in?
Heck yeah.
Yes. So that sp3 lone pair of electrons can be shifted into the ring, which means we do have a p-like atom there. What's the hybridization on that nitrogen, our bottom nitrogen? sp2. So do we have a p-like atom there?
Yes.
Yes. So p-like all the way through, with one kind of weird one that we've got arrowed. Okay. Is it approximately planar? Okay, that one's hard to tell. Assume anything I ask you, yes, it's approximately planar. Okay. How many pi electrons are in the system? So now is where it gets tricky. We've got our lone pair, or sorry, not a lone pair, a bond, bond, and that lone pair. What about the lone pair out here?
You said you can only count one.
You can only count one from a heteroatom. Is this a different heteroatom?
Oh.
Yeah. So we could possibly count that, but we don't. Why not? So what if I had drawn this structure? Would this lone pair now count? It's the exact same thing as this one. So your statement outside the structure is correct, but there's a very easy way to misinterpret it. Why is it outside the structure?
More space.
They're not available.
What orbital is holding those electrons?
sp2.
sp2. The sp2 is 120 degrees away from everything else. It's aimed away from the structure. Where are those electrons? sp3, which we can tweak slightly to bring into the structure. Okay, so the exact location of where I decided to draw the lone pair is irrelevant. It comes back to the hybridization. Okay, so as a rule, what you could come up with, or what has at least worked in previous semesters with other students, is you can go through and count lone pairs on a heteroatom. You can only count one. So we'll go with our p-like. If we have an sp3 heteroatom, we can count one lone pair. Which then gets rid of that whole outside the structure argument. What's the hybridization of that nitrogen? sp2. Okay, as far as counting our electrons, it has to be sp3. We can't count that lone pair. Okay, so if you see a heteroatom within the structure, don't immediately assume those electrons are part of your pi system. Don't assume they're not part of it. Evaluate its hybridization. If it's sp3, you can count one lone pair, which is why when we looked at our oxygen structure, we could count one of those lone pairs, but we did not count the other. Okay? So how many electrons are in our last system? We had 2, 4, 6. Is that structure aromatic? Yes. Yep.
Is the hetero atom always the 5-carbon ring?
Heteroatom is referring to something other than carbon
Not even
in your structure.
But just is it a pen?
The heteroatom is that oxygen, nitrogen.
But is it always that same structure, or?
No, it could be a 6-membered ring.
Oh, okay.
Yeah. Okay. Questions about aromaticity?
So it could be any kind of ring.
Could be any kind of ring. Okay. So as far as our summary, we've already got one up there, and then I said I won't test you on the approximately planar rule, but it's part of the textbook, so if you're reading the textbook, be aware that it does show up. Okay. Why does that rule show up? Well, this is going to look ugly, but I'm going to try it anyway. This structure, octatriene. I'm not going to put in all the numbers. Tetraene, there's 4 of them in there. Okay. This rule, or this structure, tetraene, invalidates your approximately planar rule. Okay. What ends up happening with that compound is it folds on itself and you get kind of a boat shape. Okay. How would you know that?
Because you told us.
As far as I can tell, that's the only way anybody would ever know that that structure is not planar, is because someone told you. Okay. Which is one of the reasons why I don't like that rule. Okay. And then it goes into other things with your 2, 6, 10 electron issue as well. Okay, but that's where that approximately planar rule is coming from. There are structures that if you expand them large enough that they end up becoming not planar, and this is one of them. And I've never had anybody give me a good explanation of why some of these structures aren't planar, or how you would know that by looking at a flat drawing. Okay, so I don't expect you to know that for that very reason. Okay? So it's a lot of information for very little reward. As far as you guys are concerned when it comes to these, you've got 2 answers. Aromatic, not aromatic. So it's true or false. Okay? If you move into more advanced organic chemistry, this is technically 2nd semester now. We've shifted from 1st semester. We're now started 2nd semester. You'll also get other definitions. Anti-aromatic. So if you're looking up, say, Khan Academy, he's probably going to be talking about things for a full year sequence, not the abbreviated sequence, and you'll see rules for aromatic, anti-aromatic, and not aromatic. There are 3 different sets. You're only concerned about aromatic and not aromatic. Okay? So if you go through and someone finds out that it's anti-aromatic, what's your answer?
Aromatic.
It's either aromatic or not aromatic are your 2 answers. So if it says anti-aromatic, it's not aromatic. Okay? That difference is distinguished down in that last line, coming back to the counting of electrons on it. Okay? So if you decide to look up information elsewhere, be aware, please remember, anti-aromatic is irrelevant as far as this course goes. Okay? Now we can move into nomenclature of your benzene structures, which is all sorts of fun because benzene compounds were very, very stable to begin with. So when we added different functional groups to it, everybody came up with their own common name. So there's lots of common names when it comes to benzene. Okay? Some of the more common ones, toluene, phenol, aniline, and benzoic acid. We've seen benzoic acid a few times. Okay? You can name them by their IUPAC nomenclature if you really wanted to, but you'll probably see them as the common name in each case. Okay? So be aware of that. The textbook will ask you questions where they expect you to look at that. Okay? I won't expect you to have those common names memorized. Okay?
What's the little squiggly line?
When we move to the next topic here, looking at more complex structures. Okay? Sometimes if we attach a substituent to the ring, okay, so for instance, let's add on something like this. What the heck?
It's a giraffe.
Why is that there? Go away. So all of those points are supposed to be carbons. We've got a lot more carbons outside the ring than we do within the ring. So what we end up doing is naming that compound based on the number of carbons outside the ring, and then we refer to our ring as a substituent on that structure. To name it as a substituent, we can't call it benzene because benzene doesn't end with YL. So we end up calling it phenol, not to be confused with phenol. Okay? Phenol is spelled with the YL. It's referring to an aromatic ring as a substituent. What's the squiggly mean? What I'm referring to is that whatever's attached out here, that bond is what I'm looking at. So if I take a generic example, I can attach anything out to the end of this. That squiggly just means anything can be out here. So like an R. Okay? But if I put an R there, that changes the emphasis. What I'm concerned about is this piece. This piece is named as a phenol, okay, with the YL. In case that wasn't confusing enough between benzene turning into phenol, but not to be confused with phenol, if we take toluene, we get rid of one of those hydrogens and we attach that carbon to something else. So there's our R group again. So we're drawing the squiggly again through that bond that's extending off into nothingness. Okay? Now this piece is a substituent. This substituent gets called benzyl. Okay? Not to be confused with phenol, not to be confused with phenol, not to be confused with benzene. Okay? I did not come up with these names. It's not my fault. Okay? So you are responsible for recognizing those differences within those structures. When I ask questions, you know I dislike nomenclature, so I probably won't ask questions like this. But your homework is where I've got problems to ask from. You will see these terms show up. You need to know what they mean. Okay? Questions about that? The last thing is looking at simple substituents as part of a benzene structure. Okay, and I'm pretty sure I got this on the next slide. So what we could go through and do is start to name some of these. So if we take a look at that first case. Sorry, it stopped recording a whole bunch. We can go through and name these two things. Okay, so we've got a bromine and we've got a benzene. Which do you think is more important? Probably the benzene. So we will name this as benzene. And what we want to do is name our substituent as a part of benzene. What's our substituent? Bromine. So we call it bromobenzene. That shouldn't be uppercase. All is one word. Okay? If we did toluene, okay, if we wanted to come up with the common name, or sorry, the IUPAC name for toluene, how would we refer to this one? We still have a benzene. What's our substituent? Methyl. We have methyl benzene. Okay? Make sense? What we can do now is start to make things even more complicated, because of course nomenclature always gets a little bit more difficult. We can try and name this one. We've got our chlorines, our benzene, and bromine. Again, which do you think is the most important? Probably our benzene. So we'll name this as benzene. What substituents are on it? we have a chloro, which looks like Doro now, Dloro, and bromo. Where is, or which one's going to be our highest priority? Where does our numbering start? So we'll say it's 1 bromo. Where's the chlorine? Position 4. How do we know it's position 4? Well, we get out our pen and we count around the ring. Okay? And we'd want to assign it the lowest number possible. So if we count it the other direction, we find out it's still at 4. Okay? So we get 4-chloro as our name, and just because we can in this case, which one comes first when we put our name together? The bromo goes first because alphabetical, I think. So we get 1 bromo, 4-chloro, which I have now out of space, benzene.
So when it's benzene, like you just know it's a benzene ring, so you don't have to say anything about where the pi bond is.
Exactly right. We don't have to specify where the pi bonds are, okay? Because it's benzene. We know it's so much more stable, so we spent so much time realizing that it's more stable, we can ignore the location of the double bonds because, taking a step further, let's look at the middle one. Are the double bonds always in those positions in our third structure? There's resonance, which means if we tried to name it with specifically where our double bonds are, we'd have to name it twice because our double bonds would move, changing the numbering. Okay? So we don't have to worry about referring to it based on the numbering scale. Okay? Where our double bonds are, at least. Okay? If we move to the next one, okay, our third structure here, we've got substituent, and on our benzene, okay, what's this substituent called? We've got a methyl, and we have an iodo. Oh. So we could go through and refer to this as a methyl iodo. Where are the positions? Which one takes our priority? I think it starts with the iodo on this. So 1, where's 2? Left or up? Left. Why left? It's going to give us our lowest number. If we counted going up, we'd end up putting our methyl at position 5. 1, 2, 3, 4, 5. Yes. Okay? So we could refer to this as 1 iodo, 3 methyl, benzene. Could we call it something else? Good answer on the yes. What else could we call it? What is that piece? We have toluene.
But then
I thought
how
that
do
was
you
a
name that
benzyl.
with the iodine?
1 iota.
So now the methyl is by definition carbon number 1, which means our iodo is at position 3. So we'd get 3 iodo toluene. Okay? Does it kind of make sense? Is that a hand day? No? Okay, just counting. Okay. Why not? Let's go ahead and take a look at that last one. We've got a piece here, piece here, piece here. Do we have any common name pieces that we've addressed? Do we have a methyl? No. We have an ethyl, but that's not one of the common name ones. So as far as our names go, we've got our ethyl. We've got our benzene. That was terrible placement. And we have isopropyl, or for those of you that hate common names. Okay, nobody hates common names. 1-methyl ethyl. Okay, same thing as isopropyl. So we would then, putting it all together, we could get ethyl isopropyl benzene. Oh, in our numbers. Got off all our numbers. Where are our numbers?
1 and 2.
Which one's 1? I'd put the isopropyl, but I'm not positive on that actually. Okay, and then our 2. So for those of you that aren't in the class, maybe listening to this lecture, this lecturer hates nomenclature. Look up your numbering. Okay, so as far as you guys are concerned, as long as you get the numbering right and I can draw out the structure from your name, I'm happy with it. You need to specify in your name where each of those substituents are. So we couldn't just say ethyl isopropyl benzene.
You wouldn't assume that's just the one?
You could assume one of them is, but you'd have to specify the other.
So I could do 2 ethyl isopropyl
Yes.
benzene.
Yes.
What? That just like made my brain hurt. I can't believe I said it clearly.
I thought 1 was the isopropyl.
Yeah. So what she went through and did is instead of including the 1, to specify where the isopropyl was, she said by definition it's at 1. So I don't have to label it as being at position 1. You don't have to specify your first position.
Okay, so
So 2 ethyl 1 isopropyl benzene.
okay.
Stick with that.
Yes, that's right.
Okay. So not confusing at all, right? Really straightforward. So let's make it confusing. Let's pick. Did you say sometimes I hate you?
No, oh my gosh. That's just
We'll go ahead and take a look at, actually, let's go ahead and just pick this one. So when we went through and named this one, let's go with the toluene name. So we picked for our name. We had, come on pen, work with me. 3-iodo toluene. Yes?
Yes.
Okay, and we said 3 because we said our toluene starts there. 2, 3, 4, 5, 6. Our iodine is at position 3. And we could go through and refer to each of those individual positions as we went through and named something. Okay? But because chemists don't like numbers, we decided to change things up a little bit. So what we'll do is take a look at that structure again, but in a slightly different view. I'm going to spin it, make it nice and big too. Okay. And what we can end up finding, and we'll see this when we move into the reactivity of our alkenes, or sorry, our aromatics, is that sure, this is position 1, 2, 3, 4, 5, 6. What's the difference between position 2 and position 6?
One's right there and one's over there.
Okay, let's pick up the structure, flip it over. Where's position 2? Close your eyes, we pick it up, toss that molecule up in the air, throw it around, spin it around. Position 2, would you be able to find it?
yes.
Yeah.
From position 6.
No.
So here we go. Whoops. Erase. Erase, erase. Okay, and remember, these double bonds can shift all the way around, so we get resonance all the way through the ring. Those double bonds can't be used as positions. Close your eyes.
But I'm thinking because there's something coming off of it.
What's coming off of it?
Well, nothing.
That's position 1. Absolutely, you can identify position 1. I didn't ask that. 2, 6.
Oh, okay, then no.
Okay, do you like or prefer or even have a problem if people do the circle?
No, I don't have any problem with that. We'll talk about why that becomes an issue later on. Okay, because there's resonance, you'll sometimes see people show a circle in between. I I don't really want you getting in the habit for that because you'll see why when we start to look at the reactivity of the structure. Okay? But you're fine to do that if you'd like. So between 2 and 6, is there a difference?
No.
No. Okay, well, being a chemist, I think numbers are stupid. So I don't want to refer to it as position 2 and position 6. So I'm going to say those positions are named ortho. That's just what I decided. Okay, but being a chemist, terrible with words. You've seen that. I mock Russians all the time. We don't use words. I'm going to change it to a symbol. O for ortho. So position 2 and 6 are also deemed ortho, or referred to as O. How about position 3 and 5?
You just make up a name.
I can. Close, very, very close. We make up the name meta, or
M.
M. And our last one, position 6.
I thought that was position 4.
I don't know what you're talking about. It says position 4.
Obviously not good with numbers.
Like I said,
Right.
just reiterates.
Second
Okay.
grade is so different.
So what we're looking at now is instead of referring to this as 3-iodotoluene, how else could we refer to it? We could say meta-iodotoluene, or sorry, did I say that already? M or meta-iodotoluene. Okay? So you'll see that nomenclature also show up. And it's going to become a little bit more, not really relevant, but we're going to refer to the positions on the ring as ortho, meta, and para for the rest of this chapter. Okay? If you'd prefer 2, 6, 3, 5, and 4, I guess I can do that too. Which would you guys prefer, numbers or letters?
Neither.
Both.
Is that only,
So I'll try and refer to them as each of those.
is that
We
only
refer to
applies
everything.
toluene?
No. What happens if we move to this structure? How would we name that?
Para.
Those are para. So we could call that one bromine. We said was our higher priority. So it's bromobenzene, but the chlorine is also attached. Where's the chlorine attached? Para-chlorobromobenzene. Okay. All it is a different nomenclature system to refer to those positions.
Is this only for like benzene rings?
Only for benzene rings, as far as you're concerned.
So it's always 2 and 6. 3.
2 and 6 are always your ortho. 3 and 5 are always meta. 4 is always para.
I should write that down.
It's pretty important. Okay. We'll probably end up doing a lot of practice problems on Thursday as far as EAS goes, just so you know. One thing I want to address about the benzyl substituent, what did we say benzyl equaled structurally? So it was a benzene ring and
CH2. What's the difference between a
technically a
benzyl
CH2
Oh, CH2.
connected out to an R group. This piece is a benzyl. A toluene is benzyl with R group being hydrogen. Okay, so the benzyl's a substituent, toluene's a structure. Okay? We get some interesting reactivity with that position. Okay? we'll address some, well, actually we probably won't address that much of it. If we take a benzyl structure, so if we take a look and find at very least a hydrogen attached to the carbon that's attached to the ring, and we add chromic acid, so remember your chromic acid was that really strong oxidizer that completely oxidized alcohols all the way down to carboxylic acids. Chromic acid is a strong enough oxidizer that it goes through and it cleaves all of those bonds and turns it into a carboxylic acid. So this carbon in the center there is this carbon right here. Okay? I don't know how the mechanism works, and I don't expect you to know how the mechanism works. At most, you would expect to see one problem like this on your exam. Okay? So what you, again, need to remember is that chromic acid is a strong oxidizer. When you've got that aromatic ring with that hydrogen out there, it ultimately requires that you have that carbon-hydrogen bond. Okay? It will get oxidized and it breaks everything down. Okay? We do require that bond because in this case, that bond is extremely polar. Why would that bond be polar? The carbon-hydrogen bond. So we'll highlight it in red here. Why is that bond polar?
Mumble, mumble.
What did she say?
Since carbon is more electronegative.
Carbon is slightly more electronegative, but if we had just looked at, say, something like this, put R groups out there, we don't get that strong oxidation, even though we still have that carbon-hydrogen bond. What's the difference between this structure and this structure? The benzene ring. Okay? That benzene ring has a lot of electron density in it, and we can start to shuffle electrons through it. Okay? So what I can do is take these electrons and move them downwards and push electron density through the ring. Okay? Likewise, I could have something come along and pull off the hydrogen with its electrons, which would make this carbon positive, right? How could I stabilize that positive carbon? I can move the double bond from the ring out to stabilize it. So that position, that carbon, is extremely reactive. Okay? It's going to start to polarize a lot of the bonds around it because that benzene ring can either donate electron density out to it or it can accept electron density. Okay? So that makes that position very, very special, which is one of the reasons why we come up with benzyl as a new substituent name. Okay, as opposed to just calling it by something else, okay, by an IUPAC name. Okay, does it kind of make sense? Kind of try and drag my feet a little bit. So I think we can go through the generic reaction for this. Okay, this is pretty much the whole section, or most of chapter 10, 9? 9. It's chapter 9, isn't it? Is back to reactivity. So now that we understand something about the nomenclature, we want to address something about the reactivity of the benzene. We also stated at the beginning it's not as reactive as, say, a triple double bonded structure because of resonance. Okay? So while it's reduced in reactivity, it still has some. Okay? So what we want to do is see how that reaction works. And the reaction I gave at the very beginning was benzene with bromine. And we said we did what type of reaction? Do you guys remember? We did a substitution. So here we go. This is where our mechanism is coming into play. Okay? How we did that substitution reaction at the beginning of class is the EAS mechanism. So it gets its own special name, just like the SN1s and the SN2s. So let's break down the name first. Starting with electrophilic. What does that mean? Electron loving. So we're probably looking at a species that would accept electrons. Okay? So we're looking at an electron acceptor. Aromatic, what do you think that's going to refer to? Probably a benzene ring, good guess. And in the substitution, we're swapping one atom for another. Okay? So let's try and figure out some kind of pattern that we can get out of this. So to begin with, our aromatic ring is probably going to be a first good step. Yeah, we're just going to draw it there again. Would I expect my electrophile, or my electrophilic portion of this name, to be the aromatic ring?
No.
Why not?
There's no charges. It doesn't mean.
It's not necessarily no charges. We don't need anything on that structure. I don't even really like that. Okay. What makes the aromatic ring reactive? The pi bonds. What's in the pi bonds? Electrons. So our aromatic ring is a very big source of, so we would expect it to be, if we had to come up with a symbol for it, negative. What charge is an electrophile? It needs to be positively charged. Okay? At least electron deficient. Okay? So we're probably looking at something else acting as our electrophile reacting with the aromatic ring. So let's try and come up with something generic for this. What symbol should we use for an electrophilic atom? Okay, well, I'll volunteer one. How about E? For electrophile? Kind of makes sense. What do I know about the electrophile? More than likely it's positive. So let's add that extra information to the structure. We know we're undergoing a substitution reaction, which means I've got an arrow to produce products. What things are in my aromatic ring? What atoms? Carbon and hydrogen. Which of those two is going to be easiest to substitute for? Why the hydrogen? Why is it the easiest to break out of there? What's that? It's not in the structure. To remove a hydrogen, how many bonds do I have to break? To remove a carbon, how many bonds do I have to break? 4. Okay. Which one's going to be easier to substitute for? The hydrogen. So in the process of drawing out my product of this substitution reaction, I would expect that I would get my benzene ring. I don't want to change anything within that, because if I change the characteristics within it, it's no longer a substitution. I've removed those pi bonds. And I want to substitute a hydrogen for my electrophile. Okay? So it's the overall reaction for an EAS reaction. Okay? So far, so good? Okay, where are we? I will redo this on Thursday, but we'll go through and I'll go through and show it to you now so you can get an idea of what's happening. If we draw out our mechanism, just said I was going to redraw it.
Yeah, you said on Thursday.
Yeah, I will redraw what I'm about to draw
Oh, so we were like, okay.
on Thursday. So
You're going to draw it better than that.
I will draw it better than that. We've got our benzene ring and our electrophile. Where are the electrons going to start at? If we're going to look at a mechanism, where should they start? If I'm going to draw an arrow to show the flow of electrons on how this reaction works, where's my arrow start?
In a pi bond.
Why in the pi bond?
Or,
That's the only place there are electrons. Pi bond with electrons, or electrophile that's positively charged. Does a positive charge have any electrons?
no.
By definition, it can't. Okay? So let's start with our pi bond. We'll take our electrons from that pi bond and share them with the electrophile. What we end up forming, I need to space that a little bit better. is a very, very unstable intermediate. Okay? We pulled electrons from that double bond, okay? Took them out of the structure and we put them back in between our carbon and the electrophile. So that carbon is fully saturated now, hasn't changed its charge. Lost electrons and gained them. The other carbon lost electrons and still lost them. Okay? So it's now positive. Okay? With a positive charge, that's ultimately a bad thing. So what do we do, or what do structures try and do when they get positive charge? Try and stabilize it as fast as possible. Where's the easiest source of electrons in that structure? Someone said it, the pi bond. Let's take the pi bond electrons and shift them over. What happens?
It's still unstable. You just changed the positive charge.
What's the relationship between those two structures? What have I drawn?
Resin.
I like the emphasis. We've got a resonance structure. Is that compound stable? No. So what's it do? It's going to try and find more electrons. Where's the more or the most accessible electrons? Again, the pi bond. You got to learn how to find more space in this. Okay? Still unstable. So what do? We need to move some electrons to stabilize it. Where's the easiest source? Let's go easiest source first, but yes, we're going to come back to that now. Pi bond. So we could move the pi bond back, but we already did that. So what's the point in continuing to play with resonance structures when we're done with resonance structures? So now what we've got to do is find a more permanent source of electrons. Where's the easiest source of electrons?
Hydrogen.
From that bond between the hydrogen and the carbon. We will take those electrons and put them into the double bond, or put them into the space between those two atoms, which then gives us and H plus. We've now done our substitution reaction.
Yeah.
Okay. All of the reactions that we're going to look at in the textbook for this chapter are ultimately coming back to this same mechanism. Okay? So you're going to be seeing this again and again and again and again. Okay? So we'll pick that up again on Thursday right there, and we'll start to look at what reactions can actually occur. How can we mess with this reaction? Make sure you turn in your quiz if you haven't already.